Right, this is the Finite State Machine. So finite, obviously, in this title is kind of like a set slash a value which has a set number of things. So it's a computational model for a machine which always stays in one place. Each finite state model has a finite set of cases. That means, say, like after 500 cases are done, it would just guess. So it can only ever be in one state at a given number of times, because obviously it has a finite amount of states, and obviously it cannot be moved, so you can't just put wheels on it and then just So the state of a finite machine will change depending on the current state and the input of the data. So obviously what it is in now and what comes in and out of it. If the data input is valid, the finite will terminate into an accepting state, else it would be angry. Right, a finite state machine can change, and it does so according to transition rules, which should describe what a finite state machine should do given certain criteria. So kind of like an if statement. So state transition diagrams. These are used by computer scientists as a visual representation of a finite state machine. They consist of states and transitions and always have a start state, which is kind of like indicated with an arrow. I'll draw the diagram now. An accepting state is shown by a double circle, so if there's no double circle then it hasn't been accepted. So the thing is this, and then there's a circle, so it hasn't really been accepted yet. Then this, another circle here, and this is where it reaches its accepting state, and it does a ting. While here is when it hasn't reached an accepting state, so it just goes back around and it does that. So that is when a certain state isn't reached, and here's when a certain state has been reached. Class. So the transition functions are represented by each of the arrows, with each arrow just merely signifying the start state and not a transition function. I swear to God, I will throw something out of a window. The transition functions are each represented by arrows, and the finite state machine represents the state transition diagram, which will only accept input data that starts with the numbers 11. For example, by 11 it does mean binary 11, so those kind of things. Simple. So the transition function between the SO and the S1, which in the diagram is the bit which does that and then does a ting, and then it is the ending bit of the diagram, would be described as if the finite state machine is in state 0 and the input is 1, so it moves to S1. So some real life examples would be parking meters. So in parking meters, it shows that 50p requires to be paid. Machines is only designed to take coins worth 10p or more, so bigger than 10p. If the customer first pays 10p, the machine goes from the 10p state to the 20p or the 50p, depending on what happens. So in this case it would be a 0, then it would be a 10, then it would be a 20, then it would be 30, then it would be 40, and then it would be 50. So from 0 there are 3 ways that this can go. This can go to 10, this can go to 20, or this could go straight to 50. Then from 10 it can either go to 20 or it can go to 30. From 20 it can either go to 30 or it can go to 40. From 30 it can either go to 40 and go to 50, and from 40 it can only go to 50. And that is basically the model. Very simple. And that is basically the whole premise. The finite state machine in this case would show odd partity. That is when odd totals of 1 will be the only things that are accepted. The machine has 2 states, one start state and one accepting state. Obviously here the start state is 1, the accepting states are these. There are a total of 4 transition functions which are shown in the state, obviously, and the accepted strings are stuff such as 1 1 1 1 0, etc, etc, and that is the state 3